hoping for something more wholesome, but that was the thing.
The date on there's kind of a trap anyway, right? Like,
all you could do is get it wrong.
Yeah, exactly. Like, no one's impressed if they know. And you would dance to it.
Yeah, all this fast clock speed.
All right, welcome back from the lunch break. And we will continue with Dripto, who will tell us what Google is thinking about in terms of fault tolerance for the future. Please take it away.
All right, hi. Thanks, Nico, for having me. So I'm going to give roughly an overview of QEC at Google, but sort of this talk is structured, so the first bit of it will be sort of summary of some of the things we've been looking at recently, and then we'll go into a bit more detail on some work I've done on Dropout, and then kind of end with a few little perspectives on where QEC can go in the future and like what sort of problems we think are interesting at Google, or some of. So I don't think I probably need this slide here, but just in case there's any questions about language. QEC is useful for suppression of errors. It's important. We kind of think that it's important for bridging the gap between the sorts of error rates we're going to see physically and the ones we'll need for any sort of logical computation of any note. And there are a few key quantities in error correction. You'll hear about distance and error rates and so on. But one of the ones that Google really focuses on is lambda. And I just want to sort of put the definition here just so that as I use it later on, we see why it's important. So lambda, which is defined, oh, that's not the laser, over here, is essentially the factor of improvement as you increase your distance by 2. This is the exponential factor you're picking up as you make your system larger and larger. And the important thing about this for us is that it's an intensive quantity. So logical error rate gets better as you improve your system or as you make the system larger. And as a result, it's somewhat hard to use when you're actually optimizing for performance. But lambda is really a function entirely of the code you're using and the density of errors in your system. So if I have a lambda of 2, let's say, that's true at a number of different sort of size scales. And I can think, OK, if I can keep this performance up while I make my system larger, I will see this performance later on. If I double my lambda, then my error rates will get exponentially larger, 2 to the power of d minus 1 over 2. So throughout this talk, I'll use lambda a lot. But you can think of it as basically being equivalent to logical error rate or however else you want to think about it. They're all monotonic with each other. It's just sort of a nice, convenient way for us to think about things and to communicate with experimentalists and have everything be clean. All right, so I'll start with a roadmap, because everyone loves roadmaps. So we are trying to build towards a large error-correcting quantum computer, but we're taking small steps to get there. We had our first milestone, which was this Beyond Classical experiment from 2019. And then more recently, we had a logical qubit prototype. So this was the distance 3, distance 5 experiment from, I guess, 2023 now, where we showed a lambda of 1, so basically breaking even as we increase the distance. And subsequently, we've now built a system that does get much larger as we, let me quickly close VS Code so it doesn't bounce the entire talk. Let's hope that fixes it. All right. So now we have a better system I'll talk about later. And so the next thing we're building towards is this milestone 3, so a long-lived logical qubit, which we're defining as roughly 10 to the minus 6 logical error rate per round. This isn't all the way to what we would need for factoring or something, but it's sort of a proof of concept that we can make one large, well-performing logical qubit, and then we can hopefully tile these systems together in some sort of modular way and make a fault-tolerant quantum computer of the future. And so the point I want to make with this figure on the right is how these two quantities, sort of distance and lambda, interact. So on the y-axis here, I have logical error rate, which should have been shown there. What you see is that this 2022-2023 experiment with lambda of 1, you're basically seeing a flat line. So as we increase the distance to the right, nothing happens. Whereas in this more recent experiment, you do see these factors of 2 you're picking up. And so we could, in theory, take our performance from last year and build some enormous computer and get to this 10 to the minus 6 cutoff. But what we really would like to do is improve in both system quality and scale and sort of ride one of these sharper lines all the way down to the sort of promised land of 10 to the minus 6 and beyond. And so in this talk, I'm going to talk mainly about error correction sort of like experiments that are around a lambda of 2 for now. But the hope is that we're using sort of these improvements in our devices to improve the slope, and then we can build large systems later on or sort of right now. Cool. So I'm going to first start by reviewing a few of the QEC experiments we've had come out recently. I'll start with the main one, or the most sort of notable one, which is this distance 3, distance 5, distance 7 experiment that came out earlier last year, or this year in Nature. So this is the sort of main figure from the paper. It shows a distance 3 code in red, a distance 5 code in light blue, and the distance 7 code in dark blue. And you can see that logical error rate is getting significantly better over time. And roughly speaking, we're at a lambda of 2. You can see on the plot on the right all the different possible subgrids that we considered and sort of a match to simulation. And there's a lot more in this paper that really shows that we understand our device well. We can model things. We can predict performance and match performance that we predict, and so on. And there's a number of different things that led to this improvement. So it's about 20 times better than it was a few years earlier. And the main takeaways there are that we improved our T1 time, so the qubit themselves got better. We also really worked on suppressing a few errors that were limiting us. And so I'll talk a little bit about that. And then we had a bigger chip, of course. Cool. So one of the things that we really care about at Google is real-time decoding. So we've talked about this a few times in various places. But we really think that for our devices to be useful, they'll need to take advantage of the fact that we have a very fast natural clock speed on our solid-state devices. So a single QEC round takes on the order of 500 nanoseconds. And so for a decoder to be able to keep up with that, we actually have a pretty significant engineering challenge in terms of just like software engineering to keep pace. And so we have talked a lot in this paper about how we built this decoder. It's a parallel decoder that sort of processes individual chunks of the decoding graph and welds them together in various ways. And then there's sort of two quantities of note when you're thinking about real-time decoding. There is the latency, and then sort of the, I guess, the per round time it takes to decode. And you can't really compromise on that per round quantity. You need to be faster or at speed with the chip you're building, or the chip cycle time, or else you're going to take longer and longer as you decode larger and larger blocks of your decoding graph. So we don't really mention that here other than to show that the latency is flat as we increase the number of cycles. This latency quantity itself is basically what happens at the end. So when you start having to do the last part of your chip, of your graph, or the last welding step, that causes you to have some lag time at the end. But the important thing is that that lag time does not increase for longer and longer memory experiments. If it did, you would have essentially T-state injections that would take far too long, and your true clock speed would be limited by just the decoding time before you could do the classical update on your T-gate injections. So I'm not going to talk too much about decoding today, but this is one of the main places where I think we could really have some important contributions from the theory community for how we can build better algorithms that can handle more complex decoding problems at speed. Yeah, there's a question there.
Does round mean extract one round of syndrome measurements, or does that mean multiple rounds of syndrome measurements there?
Yeah, so we mean a single round of 4 C-naughts in a measurement, basically, for a single round. And we don't really do this sort of XREC picture where we have D-round blocks. We are sort of considering decoding an entire D by D by, whatever block of decoding graph at once, or in parallel. All right. So I mentioned that there's a number of physical improvements this year. I'm going to highlight one here. Just because. Oh yeah, sorry.
So how is the latency related to reaction time?
How is the latency related to reaction time?
Yeah, is it related?
Like human reaction time, or sorry?
Reaction time by normally it's considered make a measurement. Decoding.
Yeah.
So that's which is what limits when you're doing it.
Right. So basically, the latency here is going to be that. So we measure this Ancilla qubit that's in, or logical qubit that's in the T state, and then this is the time it takes before our decoders output whatever classical bit we'll need to know what update to apply on what controlled S to apply, basically. So this is that waiting time there. So what we expect is that the clock speed of our chip will be, essentially you do a T-gate, and then you need to wait some amount of time for the decoder to actually give you an outcome before you can apply your Clifford correction and then continue. And so we want to make sure we limit this latency because that's what we're going to be waiting for a lot of the time.
Right.
Does that answer your question?
Yeah.
Okay, cool. So this is just one example. I mean, this isn't really a hardware audience, so I didn't want to get too far into just specific chip improvements. But one of the things we were seeing a lot in the 2023 experiment were these error bursts. So at some point, you would have a high energy event, a particle would hit our chip, warm everything up, and all the T1s would go crazy. So on the right, you can see that when it's sort of dark purple, that means the T1 is doing pretty well. And then at some point, we have an event hit, and you can sort of see where it hits. It hits on this sort of top left part of the chip, and it radiates outwards. And it's pretty hard to error correct around this. If your chip's big enough, you can kind of handle it. But the way we see it is this is the sort of meteor-like event that we're not trying to beat with just error correction on its own. We need to build some sort of hardware implementation to deal with it. And so you can see on the left plot, in our repetition code experiments, we were able actually to see an error correction floor. Like no matter how big we got in distance, at some point it leveled off. And if you removed this single high energy event that occurred over our experiment, you ended up replicating the linear performance you wanted. And so we like using repetition codes to sort of predict the future a little bit and see what are the sort of the next big limiting factors that we can start working on the hardware side while we get our surface codes large enough. Because we're not at distance 25 for a surface code, of course. We're not approaching this 10 to the minus 6 barrier. But we can now know this is a problem, and as I'll show you in the next slide, we've now sort of pushed this significantly far down. But yeah.
Hi, I was just wondering if Google's able to measure where that high energy event is coming from. Is it coming externally from the chip, or is it coming internally?
So those two options both kind of have very similar impact on the system. We do have some tools. I'm not sure how much we've talked about publicly in terms of like what we know it is. But I think there's a number of sources, and rightfully I think that right now we believe at that point, a lot of different contribution factors were all kind of on par. But as we'll show in the next slide, we've now suppressed a significant fraction of the lower energy, high energy events, which are maybe coming more from in-chip processes.
So are you saying for a particular event that when you have a high energy burst, you just don't know whether it's external or internal to the chip?
Yeah, I mean, like we don't know, when we say internal to chip, what I really mean is internal to the package. Like we don't know if it's something like a solar contribution versus like something from a radiating source inside. Those we can kind of figure out by looking at, quasi-particle spectra and like trying to guess, but we can't prove for certain. We can do things that make it worse, but we don't know which of those actually was the cause for that particular high energy event. Yeah.
So I heard there is this concept of quasi-particle trapping or something like for hardware, somehow for hardware enhancement that sort of limits it. I just wanted to ask, like, in terms of these different types of sources of these external burst events, would these enhancements to the hardware deal with all of them, or there are some types of events that you cannot deal with hardware? Yeah, so that's what we do here, and so the answer is that essentially this is what takes out the lower part of this high energy spectrum. So there's still, these traps and these quasi-particle traps. Basically, I don't go into the Hamiltonian physics there, but you can essentially add like a sort of gap in your etching, and you can create a situation where like it'll take a lot of energy to tunnel over that. If you put sufficient energy in, I mean, if you like microwave the chip, you're not going to get away with it by the quasi-particle trap. But for a significant fraction of the events, we are able to now deal with it. And so to show that we've dealt with this, we built this fun test chip, which had a checkerboard pattern. So half the qubits had this thing called gap engineering applied to them. Basically, we added these traps to our hardware, and the other half of the qubits did not. What you can see is that when this animation clicks again, right here you can see that checkerboard appears. So the qubits that are gap engineered do not really have any impact from this event. So it's still hitting the chip. It's still causing problems, so to speak. But the quasi-particles that it's generating aren't able to interact with our qubits because they get trapped out. And as a result, as far as we're concerned, the problem is dealt with. This can be overcome with sufficient energy, of course. How frequent are those high energy events that you cannot block out with this gap?
So our error floor went from 10 to the minus 6 to around 10 to the minus 11. or so. We believe the new ones are also high energy events, but there's a second floor around that area that maybe is not high energy related, it seems. Or at least we were not able to find a thing to cut out and replicate performance. So at least a few orders of magnitude of suppression now. All right, so this is one example of a thing that we've improved on. There's a number of other ones. For example, leakage is a very concerning error for many error correcting platforms. In general, the scariest hardware errors for error correction are ones that we on the error correction side don't really think about. So things like leakage, things like significantly antagonistic crosstalk models, heating in ion systems, for example, are all cases that we tend not to worry about too much on the theory side. And so those are the ones that invariably we kind of hope the experimentalists can deal with. So I'll talk a little bit later about something that we can do for leakage using an interesting QEC theory idea of walking surface codes. But in general, improving on things like leakage is one of the other places where we significantly saw wins for this experiment. But I now want to move past surface codes, or at least sort of traditional surface codes, and talk about a few other sort of grab bag interesting experiments we've done at Google. So we had 2 papers come out, I think, on the same day last year in December. And so one of them was this color code result, or set of results. And so we had, on our distance 5 or distance 7 chip, we put 2 color codes. And so we were able to compare a distance 3 and a distance 5 color code and show a lambda of, I believe, 1.5 or so. So we have a color code that's also below threshold. To get the color code to work, we did have to kind of rectangularize it. And so there's a bit of additional machinery to get certain hardware constraints satisfied. But for the most part, this is the color code as we all know it. We're also able to do Clifford gates and then show sort of interleaved IRB. And we get an average error per Clifford of about 0.0012. And then we're also able to show state injection. So this is like the first step to cultivation, which I'm not going to talk about a ton this talk, but this is the initialization of that routine, right? Getting a magic state in a T gate, or in a color code. And so we were able to show injection and show some nice Rabi flops and so on. And then because we had enough space, oh yeah, Dolph.
So here for each, so these are single qubit Cliffords, right?
So far here, these are all single qubit, yes.
And then you do 1 QEC round per Clifford, or?
Yes, 1 QC round per Clifford. But yeah, these are all single qubits, so some of them are like, transversal X gate something, but they're all pretty simple. And then we also had some 2-qubit logical experiments with these color codes. We were able to show lattice surgery and use that to teleport a qubit or a state from L1 to L2 with a state fidelity of somewhere in like the high 80s. So this is including both the MXX, the updates, and the final measurements. So there's, this is the whole circuit fidelity, not just for the operation of, merge split. But we're able to see the same performance, and it's nice to prove out that we can do all of these things in color codes as well as surface codes. And again, this is still operating below threshold, although because the color code threshold isn't as generous as surface codes, the performance is reasonably worse. And the decoding problem also is much harder, which Noah, who I just saw walk in, could tell you about. We also had these dynamic circuits results for surface codes. So there's a paper that I mentioned here at the bottom, McEwen et al., from a few years ago, where they discuss a number of new circuits to measure surface codes. So the standard one is kind of just the one that we all know. And then we have one that exists on a hex lattice. So every qubit only talks to 3 of its neighbors instead of 4. This has experimental implications. We can make an easier chip, essentially. There's also a walking surface code, which is really fun, because it moves back and forth. So it drifts where measure qubits and data qubits swap roles, and it kind of moves a half step each round. We also have ones that move a full step each round. And this is really impactful for leakage. So leakage is a sort of error where a qubit leaves the 0-1 subspace and instead goes to a higher level. And for measure qubits, we're not too worried about it. We measure our qubits out, we reset them, and this can extract leakage over time. But for data qubit leakage, we just have a qubit that's sitting in a state we don't know about, we're not trying to control properly. It ends up dephasing its neighbors pretty significantly. Leakage can move around and spread. And it ends up being a significant impact on our system. You can see detection fractions that go up. I believe in 2023, they went up about 12% over the course of 25 rounds. And so the nice thing with a walking surface code is that you can have it oscillate back and forth, interchange the measure qubit and data qubit roles, and every qubit is now measured every other round. So if there's any leakage, the lifetime is now significantly shortened. And performance-wise, you don't take too much of a hit. We also have an example of a surface code where you can use ISWAP gates instead of CNOTs, which for superconducting qubits is nice because our ISWAP never leaves the 0-1 subspace, whereas our CZ gate actually does. And so CZ gates tend to be leakier. So this is another case in which a nice theory improvement allows us to maybe have an easier time on the experimental side. And then we also, in this December paper, ran all these experiments and took, that's where the mouse went. And then took these lambda measurements. So we have a lambda of 2 for the 3-coupler hex surface codes. You should basically think of these as being almost identical to the regular surface code. Like one CNOT gate is flipped in direction, but otherwise they're pretty much the same CZ layers and everything. The walking surface codes had a lambda of 1.7, and the ISWAP surface codes ended up having a lambda of 1.56. So all 3 of these examples are below threshold. But what I'm sort of want to point out here is that all of these are surface code circuits in some general meaning of that term. They're measuring the stabilizers of the surface code as we would all describe them. But what I want to kind of argue in this talk is that codes maybe aren't the most fundamental thing for us to be thinking about. When we're going to be using a circuit model, the actual circuit you're using to implement the code is a significant contributing factor to how it performs and what results you get out of it. And so we really should start thinking about error correction kind of in more of like a code first or circuit first way, where we think not only about what stabilizer we're extracting, what detectors we're making, but how are we actually doing it, what circuits we're using, and more thinking about detecting regions in this like 2+1D picture. So I'll talk more about this later on, but I think this is one of the things I want to have sort of everyone take away, is that there's a lot of interesting sort of work that we can pull out there, which maybe if you think about things sort of purely theoretically doesn't really matter. It's like if you have a bunch of surface code circuits that all do the same thing, who cares? But experimentally, we often see significant benefits from using one versus the other. So for this hex grid surface code, even though it's performance-wise identical in threshold, it has less 2-qubit gates for us to calibrate. So you can imagine that being easier to build or calibrate, or you might get some better 2-qubit gate performance if using that circuit instead. OK. So with that, I'm going to kind of move towards QEC theory advances. So I guess I'll have some questions here if anyone has any more questions on the experimental side. Also, when did we start?
You have like 3 or something.
Oh, cool. All right.
I have a question.
Oh, yeah.
Do you have methods to analyze these circuits? Not by just simulating them, maybe more advanced one?
Yeah, so I would say the tool we use for most of our circuit analysis is STIM, but that's mostly a simulation tool. However, STIM also holds all the detectors, can build you the decoding graph, and so on. And we have added some tools to the public version of STIM that do some of this analysis work. One of them is, I don't know what the method name is called, but basically it makes detecting regions, which are kind of what you can think of as, I'll show these later on, but kind of like the 3D volumes in space-time that are, a single detector is sensitive to. And this is probably, I think, like kind of the extension of what stabilizers are. So instead of thinking about a detector as being like, I compare this stabilizer and the same stabilizer measured the second time, once you think about the actual circuit, what you really are doing is looking at this Pauli operator as it propagates through a circuit and closes back up. And anything that flips the eigenvalue of that Pauli operator is going to be detected by that detector. And I think STIM does have a tool that gives you all the detecting regions factored out for your circuit. So analyzing things like that oftentimes can be pretty productive. Yep. And there's also visualization stuff that I'll show as we go through this. All right, cool. So I'm going to flash up some cultivation stuff here, but Craig already gave a talk at Simon's about magic state cultivation. So I would refer you to that talk and say that he probably will do a better job than I would do for cultivation. However, there was this paper from this year, or last year, I guess, where we talked about how you can use a sort of color code, surface code hybrid system. I believe they use the term grafted to get pretty high performance T gates or T states into a surface code boundary object using a number of different tools. So there's injection at the bottom here, and then this cultivation stage where we gradually have the code get larger and larger before escaping into a surface code, measuring for a number of rounds, and then using a complementary gap to actually further post-select before we give you the final state. And I'm not going to go into too much technical detail on it. It's a pretty involved result. But what I'll say is that it's nice in that it bridges this gap between injection and distillation. So in the past, there was, so here on this plot, I have cost on the bottom on the x-axis, which is just qubit time rounds. This is a figure from that paper. And the y-axis is logical error rate. And these points over here and the points down here were already known results. But there wasn't this region in the middle that cultivation has added in. So it sort of was like a discontinuity where if you wanted a certain quality of T-gate, you suddenly needed dramatically more resources. And this has kind of shown that, no, there is, in fact, a kind of smooth transition between these two regions, which is nice, increases our confidence that we understand what's going on. We've not maybe squeezed things as hard as we could, but at least we've squeezed at every part of the curve equally. And in general, this result's nice because it is very friendly to our current architecture. It is 2D nearest neighbor. It doesn't require any extra pieces, any additional bits and bobs. And so there's no reason we don't think we can just do this, sort of if we had a large enough system. OK, so with that, I'm going to talk for the next while about this paper from last year about a technique called Lucy, or a framework called Lucy, which really is a way of thinking about adapting surface codes to grids with dropout and fabrication failures. So in sort of the theme of experimentally relevant error correction, the majority of error correction results we'll see in the field assume very nice, well-behaved lattices. We say, I have a square grid of qubits, and then you assume you actually get a square grid of qubits. But the reality is that when we're fabricating these devices, things break. And as we build larger and larger systems, for all the surface code experiments you've seen so far, we just built chips until one of them yielded perfectly. We weren't going to accept a broken qubit in the middle. But as we get to larger and larger systems, we need to start designing methods to actually adapt a surface code to an imperfect grid. And this technique really is focused on finding that problem. In the process, it essentially creates an infinite family of surface code-like circuits. And then you kind of just try to find one that in that family that fits your particular section of failures. So to do this, we'll use these detecting region pictures that I was talking about earlier. And so the key insight for all this work came from this initial paper that I was talking about, McEwen et al., where they talked about how if you look at a regular surface code and you propagate all the stabilizers halfway through the circuit, you end up with an unrotated surface code state on data and measure qubits. So you have a regular surface code where all of these stabilizers are just on data qubits. You then reset a bunch of measure qubits, so you add extra known Pauli eigenvalues to your setup. And then you propagate through 2 rounds, and you end up with twice as many stabilizers because you now have the stabilizers that are here that are closing up as well as the new ones that are opening. And what they kind of realized was that instead of thinking about the original surface code picture, you can instead focus on this mid-cycle and try to measure all of these stabilizers in place. So what I mean by that is, measure this MXX, reset it, and then expand that back out. And if you do this in the right way, you end up finding a number of different ways to measure the surface code that all give you the same distance, roughly the same performance, and so on. But you can be flexible about how you actually pick your gates. And so the example I'll explain here is the hex grid surface code, or this 3-coupler one, where we don't use 1 in every 4 2-qubit gates on each qubit. And so I'm going to explain it using what is called a Lucy diagram in this paper. Essentially, the backing checkerboard is the mid-cycle stabilizer group of this particular circuit. So again, I'm not going to say code because different circuits for the same code could feasibly have different mid-cycle states. But for this family of circuits, we'll use sort of the usual checkerboard here. And then the individual shapes that are drawn are the ones that are going to be measured in that round. So we're going to go sort of like an A-B type setup. And then each of those individual shapes can be compiled down as follows on the right. So this particular U shape will be, the dot shows the qubit that's measured, And you're going to propagate all of that x information down to that mx, measure it, then reset it back out and expand back out. And so in each of these squares here, I'm going to measure, for example, the zzz eigenvalue of that particular blue square. And then I'm going to reset and prepare a new zzz Pauli operator as well. Yeah.
Sorry, what do you mean by cycle here? Just cycle to measure? Or?
Yeah, I just mean like this is sort of one round and this is another round, and you're kind of alternating between the two of them. But the tricky thing is we've now kind of shifted our definition of a round kind of by a factor of like halfway through what we normally would. So normally, if we say a round of error correction, you mean one stabilizer extraction of this n cycle stabilizer. So you mean like I'm going to measure all of the stabilizers in like this area here. But what I mean here instead is I'm going to go from mid-cycle to mid-cycle, and then I'm going to kind of repeat that again and again, where the cycle is just the sort of 4 CNOT layers of the usual surface code circuit.
I guess maybe I'm confused why the code is changing a little bit.
So they're Pauli operators, right? So it's just propagating through. So the statement is that or the idea is that basically instead of thinking about error correction in terms of a stabilizer group and then measuring it, right? What you're really saying is I have a state at this particular time point that has these stabilizers. And then as you apply Clifford operations to it, those stabilizers are changing. So halfway through, you don't have the same stabilizers and the same qubits as you did before, right? They've propagated somewhere else. And so this is basically just tracking that full propagation over time. So that's why they're changing. And then the particular ones you're extracting in one of these 2 rounds is just because you can't measure them all at once. If you did, you'd be measuring d squared minus 1 operators, and you'd have 1 qubit left over at the end. OK, so the important things to note here are that basically these shapes tell you what mid-cycle stabilizers are being measured, and also how they're being measured, according to this sort of compilation on the left. And the gray lines are the 2-qubit gates being used. So for example, this pair of qubits never talks. And so if you were actually fabricating a chip for this particular circuit, you could not include that 2-qubit gate and build a hexagon instead there. And that's the general idea for this 3-coupler surface code. We're going to take the same idea for Lucy, and we're going to instead sort of use more different rounds in order to further interleave things in time. And that's because we're going to be trying to avoid certain broken components, and that's going to limit how we can actually extract certain eigenvalues. So to understand why we need to do that, we first need to explain what makes these shapes allowed to be next to each other or not. There's these rules to how these boards fit together. And so here on the left, I've shown sort of like a zoom in of 2 squares in this checkerboard. And you have these different shapes that connect. And then on the right, I've shown the compilations they actually correspond to, where the numbers next to the gates are the layers in the circuit where they would occur. And you can see that here, the 2 qubits that overlap do agree. And so we're all good. This is allowed. But in the other 2 examples, the red highlighted gates are colliding. And so these 2 shapes cannot fit next to each other. The eventual outcome is that you need to follow this sort of snake pattern, like sort of a zigzag. Anything that doesn't follow that will require you to space these 2 measurements out in time. So if I really, really need to measure these 2 U-shaped operators next to each other, I need to measure one and then the other at a later time. I can't do them at the same time. And that's kind of how we're going to get around a lot of these broken components. We're going to measure things at different times. We're going to measure sort of different pieces of them different numbers of times. So occasionally, some stabilizers will be measured more often than others. And this will allow us to extract as much information as possible from our system, extract as much entropy without ever really requiring ourselves to use a broken component. So this is all pretty kind of complicated and abstract. So I want to try to build an example that will make sense. This is still admittedly a bit arcane, and so I would recommend that if you're interested in this sort of thing, to really look at the paper and sort of see it all laid out a bit slower. But imagine you have this distance 9 grid with 4 broken qubits and then a number of broken couplers as well. So the red X's are broken qubits, and the red dotted lines are broken 2-qubit gates. The first thing we're going to do is remove this qubit where these 2 broken couplers touch It turns out this isn't fundamental, so you'll see some future work, hopefully very soon, that will show how you can get around this. But in this case, I actually just removed this qubit as well. And then we cut this out of all the mid-cycle stabilizers. And so what you now have done is you've demoted a few of your stabilizers to gauge operators. So whereas all of these squares in the bulk commute because they each share 2 qubits with anything of the opposite color, around this boundary here, you have a bunch of weight 3 triangles that anti-commute. And so we're going to have to pair these up. So this is sort of the standard subsystem code approach. You pair things up as appropriate. And you now have these gauge operators that you need to measure. And you'll need to measure them in a sort of careful order where you measure both the x ones before the z ones. Otherwise, they'll anti-commute and remove themselves from the stabilizer group and so on. So once you've done all this grouping, you can find logical operators. And so you can find them just in the mid-cycle. And then because over time they'll propagate through and form a sheet, you can just find them at one time slice and then infer them the rest of the way. So this sort of 2 plus 1D picture promotes all your stabilizers to these 3D volumes and your logical operators to these 2D sheets. But you still can really think about things in terms of a cross-section, at least to get your bearings down. Once we've done this, we actually need to build all of the rounds that will extract this information. And so we start with sort of a base footprint. It's kind of hard to see, but this circuit corresponds to a circuit that is almost identical to the usual surface code circuit with 2 key exceptions. The first is that the footprint has been modified. So normally on the surface code, you have this weight 2 stabilizer, then a gap, and a weight 2 stabilizer, a gap. So the measure qubits on the boundary have kind of a jagged, like off, on boundary. Here we're filling them all in. These qubits end up being useful routing. Like if a coupler is broken, you need to maybe go around it in a different direction, and so it's useful to have those qubits there. The other thing is that all of these circuits I've shown you, or these half rounds, they're self-reversing. So you use the first 2 CNOTs to get to the measurement, you reset, and then you reverse those 2 CNOTs you just did in order to push the information back out. And so as a result, the surface code that you're running here will have its 2 qubit gates reversed every other round. So if the usual surface code CNOT layers would be ABCD, 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 this will be ABCD, DCBA, and so on. The impact of this on the actual circuit is relatively minimal. It makes your detection regions a bit asymmetric. They kind of look like trapezoids instead of diamonds. But all that really means that if you have like a significantly anisotropic noise model, you'll have some oscillatory behavior in your detection of infractions. But it's not a big difference. Once you've taken this sort of initial circuit, you first remove all the stuff that touches any of the broken things. And so, for example, here, the measurements that we're going to curve, we're going to use this broken qubit, so we'll remove them for now. In some cases, the weight 4 measurement I was about to do never used the broken coupler. So in those cases, we'll leave it in. And then we're going to start trying to fill things back in. So in order to maintain the distance of this code, I need to measure every single one of these squares in one of these rounds. And so depending on the dropout configurations, there might be initial starting points that are better or worse than others. But for the most part, it's kind of a simple game of applying a 4 coloring to your square lattice. And then because of this 4 coloring, you can now not make sure that none of these red squares, for example, touch any other red squares. So I can put whatever I want in each of these red squares, and they'll never conflict. You're kind of just trying to find a way to get everything to agree and not conflict. And so you apply a constraint that you need to follow this particular coloring. You remove stuff, and I mean, this is a bit more well explained in the paper, but the idea is that you can kind of guarantee that it's possible to find a solution to this problem that will still end up with a valid measurement of every single one of your rounds. And because of the structure of these circuits, they'll always still be matchable. They'll still have all the nice properties of surface codes. They should have the same boundaries. Lattice surgery should be fine. All of the things we know and love about regular surface codes still work for these things, even though, as I will show you, the actual circuits end up being kind of unfortunate looking.
What does
sure.
high error rate detectors mean?
What I mean by that is, so when I have a detector, I'm measuring, let's say, a given stabilizer generator over and over again, we think about the detection of infraction a lot, and detection of infraction is defined as what is the likelihood that this particular detector lights up in a given round, right? What is the chance that a stabilizer eigenvalue is flipped? And so if you have a measurement that only occurs once every 4 rounds, it's lasting a lot longer, and so you're going to have, like, instead of a 10% chance of having it flip, you'll have like a 30% chance. So the problem there is that you're extracting less information. You're just like getting less information out of that particular measurement because it's already kind of randomized. And so that's bad for your decoding problem. And also, because that stabilizer is alive for so much longer, it ends up forming a node in your decoder graph that connects a lot of things together. And so you end up having sort of these shortcuts in your time-like distance as a result. So when you're doing lattice surgery, the number of measurements that you need to repeat actually might increase depending on how you do this.
Thanks.
And then you get your question as well.
Yeah, so this 4 colors are enough for any configuration of dropouts, or just because it's 5 here, you have like or 6?
Yeah. So let me go back into this in more detail then. So the idea of this 4 coloring is basically that with this particular square lattice, none of the, let's look at the red one, because it seems like it's showing up best on the slides. None of these qubits here touch any other red square, right? So whatever I put into like this shape here, I can put a different thing in here if I need to for a broken qubit or coupler and whatever. So the 4 coloring works for the square lattice just because it has that property. If you're trying to replicate this on a different fundamental lattice for like a different code, you might need to do a different coloring scheme. And it ends up that this can be improved on. This is kind of like just like sort of a upper bound on how bad it can get. But you can do better than this as well. Does that make sense?
Yeah.
Great. Any other questions here? Yeah, I appreciate this part is like relatively confusing, so feel free to ask questions if there's anything coming up. All right, but once you have created one of these diagrams, the actual compilation to making it into a circuit is pretty straightforward from here. All the CNOTs and stuff are defined by just the shapes, and then to actually find the detecting regions, you can essentially just propagate Pauli operators through a Clifford circuit and get the outcomes you'd expect. So to do that,
I just have a question about something you said earlier, that the detection fraction oscillates.
Mm-hmm.
So does that mean that like there are times where the errors are much more likely to happen, and then there are times where you're kind of safer? And so then could you kind of like shrink the code in the safe time?
What I mean by that more is that if you had like a particular qubit that's really bad, instead of having equal sensitivity to that with each of your measurements of a given detector, you would instead have sort of like either less sensitivity and then more sensitivity and less than more. So it's more about a statement of the individual detector instance sensitivities to a given qubit than it is about like the actual error rate of anything like that. So I don't think you could do anything adaptive there because it's sort of symmetric. Like if it's good in this round, it's because the next one's going to be bad. And then similarly, the other sort of stabilizer that's touching that qubit would be bad and then good, I think. Because I don't think it'll actually be, I don't think you could do anything particularly clever there. But I mean, we can talk at some point. But yeah. Cool. So I want to kind of bring this detecting region point home a bit more clearly by talking about this example. So here I have 3 rounds, and we're going to focus on this mid-cycle stabilizer in the middle here. And we're going to start halfway through this round. So there's a reset, and then there are two CNOT layers, which will propagate this single Z Pauli operator to await 4. We then go into the next round, where this particular square is not measured. So it's pulled in some strange directions, hits 2 Z measurements, which are then added to the eigenvalue of the detecting region. The resets are then added in, and then it comes back to itself. So because all of these rounds are self-reversing, you're sort of shrinking things down to a particular qubit, measuring, resetting, and then expanding back out the same path you took. You're guaranteed that you'll always come back to where you started in a given round if you're not being measured. And so all we need to do is propagate a Pauli operator through a Clifford circuit, see what measurements it hits, and then we know we come back to the same place. And then this third round, we're going to again measure that square out, and so it collapses down to a single measurement here. And so the eigenvalue of this detector, or sort of the equivalent to a comparison of 2 stabilizers in the regular surface code, ends up being the comparison of these 3 measurements on 3 different qubits in this particular example. And so what I kind of wanted to highlight here is that this is sort of an easy procedure to follow. It's not as easy as just compare this measurement and the next one on the same qubit, but it somewhat follows the same structure. And these 3D volumes, or these 2D time slices of a 3D volume, are essentially the equivalent of 2 stabilizer measurements in the regular surface code picture. So when you combine all those together, you have what we call a detector slice diagram. So we've been using these a lot at Google for the last few years. I know the rest of the community does not think they make any sense. But my hope here today is I can convince you that these are, in fact, useful. So, I mean, admittedly, this one's kind of stressful. And so I'll use it to first point out that sort of like the promise of Lucy is that all the complicated nightmares in the middle here, where you normally would hope to see a regular surface code, are very messy. But the sort of goal of this whole method is that the mid-cycles are instead well-behaved. So these are kind of nice and easy to look at. And then all of the stuff in the middle is automated, and you never have to touch it yourself unless you really, really want to. So that's the first thing. You'll notice they have surface code boundaries, even though they're kind of weird looking. In the bulk, they don't look super surface codey. But then at some points when there's not too much modification from the traditional circuit, they do look pretty standard. And then at the ends, they look as you'd expect. Now what this picture is it's every single detector in the circuit having a cross-section cut out of it every single layer. So it can tell you things like, for example, I can look at this area and see, OK, this is a large red, this red region on the bottom here. That's pretty large, and so maybe that's going to be a detector that's noisier in some way, right? It's really sensitive to a lot of qubits right now. And what you can see is that because this maybe is not easy to verify in the moment, but you could pick any qubit on any of these slices, and it's only ever touching 2 red or 2 blue stabilizers. And so that's kind of the promise that we're having a matchable graph problem. If you were touching 3 or 4 red shapes at once, that would mean that you now have a hypergraph decoding graph. So yeah, the goal of these detector slice diagrams are really good for diagnosing things, and they're really nice for finding sort of these hidden structures in these circuits we're using. So despite the maybe startup cost of thinking about them, these are sort of what I would argue are the sort of next step of beyond sort of a stabilizer diagram of a code. In terms of performance, we do far better than previous state-of-the-art. Since the paper came out, a paper from Amazon came out that approaches Lucy's performance. I believe it's slightly lower in distance, but very, very comparable. But this came out when the previous methods were a bit older. And so in comparison to, I would say, this method, which is from 2017, I have first on the top here heat maps showing distance. So these are all for a patch diameter 15 footprint chip with qubit dropout rates between 0 and 2%, and then coupler dropout rates also between 0 and 2%. And so if we focus on, say, this 1%, 1% square, Lucy is able to achieve a distance of, on average, 13.1 versus 9.1 for previous state-of-the-art methods. And then this distribution on the right here shows that, again, Lucy is a pretty dramatically improved distance, and it's narrower of a distribution, which is nice because it means that your sort of worst-case scenarios aren't as bad. So hopefully that means you wouldn't have to throw out as many of your chips due to them having some sort of antagonistic dropout pattern. Yeah.
Is distance literally the shortest operator, or it's how the error rates scale?
Shortest operator. Yeah. So yeah, so you can think of the top as like sort of worst-case performance type behavior. And yeah, I want to give some intuition on like why it's better. There's sort of 2 key points. So firstly, previous state-of-the-art methods lost 2 distance for a broken measure qubit, 1 for a broken data qubit, and then 1 for a broken coupler, because they just removed the data qubit attached. Lucy only loses distance for broken data qubits, and it just loses 1 distance. So you have a strictly better performance there. You can see there's a big asymmetry in Lucy between couplers and qubits as a result. So we have these sort of vertical stripes. And then when we actually simulate this, we simulate this at 1% SI1000 noise. And this ends up corresponding to roughly a 40x improvement in logical error rate. So compared to a dropout-free case, previous methods had a 600x improvement, or not improvement, 600x higher logical error rate, and now it's like a 15x penalty instead. So again, don't break stuff if you can avoid it. But given that we think we probably can't avoid it, we'd rather have it be as cheap as possible so we can push on other things instead experimentally. Okay, so cool. This is, yeah, I just have some like final thoughts now. So I kind of wanted to give a few takeaways here in terms of useful things that we're thinking about a lot at Google and like sort of tools we are more excited about. So we really do think this sort of circuit-centric QC ideas are very valuable. Understanding things in terms of detecting regions allow you to kind of understand how does a walking circuit actually work? Like how does this measurement get moved down somewhere else? How does how do you run a surface code with just 3 couplers instead of 4? And so the original paper from Matt, I think, explains the ideas in like theoretical detail. That's very nice. But also, I really would recommend reading this experimental paper because they kind of condense a lot of the ideas into sort of simpler and more, I don't know, easy to digest ways, which I think has its value for sure. And then building tools and frameworks that really allow you to work on this is going to be very useful for improving our ability to do this kind of research in the future. So Craig, as probably everyone here knows, is a big fan of making sort of custom tools for things he's working on. And so to this end, for this sort of stuff, he's developed one called Crumble, which you can find on his website. You can find links to it in all of his recent papers. And that's kind of what a lot of us are using now to do some of this work and really analyze circuits deeply at the circuit level. But I think that if this community at large can start thinking about these things and finding better ways to look at these pictures, I think we'll have a lot of benefit to it long term. And then, yeah, this is also very useful for thinking about things that are optimized for experiment. I think as theorists, we often like to keep things very simple, but also abstract. And at times when you actually try to make those abstract ideas sort of fully crystal clear for an experimental, like sort of implementation, you realize there's a lot of constraints we didn't realize. And being able to understand things at the circuit level means we can find cheap ways we can modify the circuits that matter a lot for the experimentalists, even if for us as theorists, the simulation number at the end of the day is the same, so we kind of don't worry about it too much. And the other thing is that there's lots of headroom still available in these 2D nearest neighbor architectures. So we heard in the talk from Eddie earlier about these bivariate bicycle codes and how you can think about LDPC codes and all the incredible advantages you can get there. But we really do think that there are a lot of simple, sort of straightforward improvements that we still don't know about at the sort of square lattice chip level. And so we're kind of focused right now, at least, on seeing how far we can squeeze that. So here are a few examples. The cultivation experiment I talked about earlier, as well as this in-place Y measurement. And then this is another sort of simple follow-up to Lucy I wrote, where we were able to show that we can do a surface code on a heavy square lattice, so a lattice that has qubits, a square lattice that has qubits on vertices and edges. And so you basically only need half the measured qubits in the traditional surface code circuit to run a surface code. It's worse as a result, but experimentally that could be of interest. And so just sort of the idea is generally that we're not capped out here. This is all just stuff from the last year or so. And there's probably a lot that we haven't found out yet as well. And then final thoughts, there's exciting work going on. QEC at the circuit level is important. And then in general, we're now entering this era where, as we saw in the first talk, there are experiments, right? Like all of these talks have had some experimental component. And so we're now really entering the time where theorists thinking about experimental constraints and realities and vice versa is becoming more and more important. Like we don't really have an excuse anymore to be doing purely theory for theorists' sake, unless, that's what you want to do by all means. But like there now is experimental structure that we can take advantage of, we can learn about, and really optimize for. And we really should be trying to take cues from the experimentalists and vice versa. And then here's a picture of the team that's a few years out of date, but the most recent one we have. So yeah, thanks.
All right, do we have questions for Dripto? Yes. No.
I was reminded of this paper by Baskin and Kubica on morphing quantum codes, where they take like a color code and they put a patch of surface and put it in, or vice versa. And I was just wondering if Lucy, if there could be any connection where you take color code with dropout and turn a patch of it into a Lucy code or something like that.
Yeah, I mean, I haven't thought about color codes too much. You definitely could do that for the surface code bits. The color code bits would be tricky. But more generally, there's this other morphing circuits paper from Mackenzie Shaw et al., where they also looked at these sort of mid-cycle like constructions, but for the bivariate bicycle codes. And I think they're able to remove one gate layer as a result. They had some improvement to the circuit as a result of that. And I think that in general, as we start thinking about, for example, a color code, surface code like hybrid circuit as a circuit that is fault tolerant, as opposed to a color code here and a surface code there and some amorphous stitching region that we don't really talk about and explain as well, I think that we'll be able to find things like, oh, I really just want to get that operator to over here. And there's a number of ways for me to do that. And if I don't have this particular coupler available to me, maybe I need to use a different path. But if the problem is really just get this operator over there and get that one over here at the same time, that's an easier optimization problem than kind of giving you an abstract picture of here is a color code, which is an object we all know, and a surface code, and then some stuff, And so hopefully I think that as we sort of develop these ideas further, that's kind of where you'd hopefully get. You'd like to get to a place where we're just talking about fault-tolerant circuits and fault-tolerant protocols, and it's kind of abstract how exactly you do that, but maybe codes are the best way of describing it, but there seems to be something more fundamental than that.
I have a somewhat philosophical question along these lines.
Okay.
So I guess in my talk, the theme was, okay, identify mechanisms and then do only what you need. I guess it's very similar here. I like what you just said, oh, you want to move this operator. How do you move this operator? Is there a sense in which we can kind of morph the language, if you know what I mean? Maybe it already is the same language, but I very much agree with what you're saying. Once you make it so pragmatic, what's the goal? Then there's always shortcuts you can find.
Yeah, no, I think that I think there's a lot of, it's kind of sort of I guess because we don't have shuttling and we don't have, kind of the sort of nice clean ways of being I'm going to move this over there by just moving that thing over there. We have to do this sort of circuit stuff, which I feel almost is the same overall goal with the opposite direction, where you often show this picture of, here's, this logical circuit I drew out just as a logical circuit, and I just implement them as if those logical qubits are physical qubits. And I'm kind of arguing, no, we should think about that whole algorithm as a circuit and then do weird things at the microscopic level to get it all to work out. But the end goal is still that we kind of want to be able to zoom out and just think of an algorithm as just here is the logical circuit I want, and I'll thicken out those lines in some way that is maybe hopefully automated and then get there. But I think, yeah, I'm sure this language has some sort of overlap. I don't know if all the things that the circuit side could do could give you all the things you want to do and vice versa. But I mean, if you think about swap as a circuit operation, then you can do a lot of things.
Any more questions? Okay, if not, then let's thank Dripto again for the very nice talk. We have a very short 15-minute break, and then we will return with the panel discussion.